Hello, everyone. In this lesson, I would like to go over um, two questions. One is how to apply piecewise functions situation in the limit, especially one-sided limit. Okay, so how do we see this, right? So we have function. There's three pieces, right? It's a piecewise function. So from number lines perspective, okay. I'm going to first explain this, and then second, I will show you how you show your work. Okay. So you have this that we have this number line. There are three intervals. Okay. There's a point zero. There's a point zero, and there's a point pi. So these are the two places where the three intervals are being cut. Okay, 0 pi. For less than 0, the function we use is 1 plus sine x. Okay, so you're gonna mark it 1 over sine x. So you don't really have to draw the whole picture. Okay, and second piece is between 0 to pi, and that function is cosine x. And the third piece is sine x. The sine x. Okay, how about the points in between, right? How about the point 0, for example? When x equals 0, you can see this definition shows that if x equals 0, we're going to use the second rule. If x equals to pi, we're going to use the second rule. Okay, for x less than 0, does not include 0. For x, you're going to use 1 plus sine x. For x greater than pi, does not including pi, you're going to use sine x. So in this process, we expect to see that you understand the piecewise function, and you also understand how to express one-sided limit. Okay, so this simple graph will be serving as a simple example to help us. Okay, you don't need to really show that to the teacher or the reader as long as you know. So let's look at the first one. The first one, as x approaching 0 from smaller than 0, obviously we are approaching 0 from smaller than 0 from this side, right? If I put an arrow, we're approaching 0 from smaller than 0. So that's the setting. That's the setting. And which rule does it apply? The rule that applies to the situation is 1 plus sine x. So 1 plus sine x. Okay. Ideally, put in the parentheses, and in terms to find the limit of 1 plus sine x, it's a direct substitution. So it's 1 plus sine of 0. Sine of 0 equals to 0, so the limit equals to 1. Second, x approaching 0 from larger than 0. Okay, so approaching 0 from larger than 0. So in this interval, between 0 to pi, so the rule is going to be cosine x. Okay, so x approaching 0 from larger than 0. Okay, you make sure you mark it properly. And this is once again is a direct substitution cosine 0 that equals to positive 1. Limit from left equals to 1. Limit from right of 0 equals to 1. Therefore, the limit is equals to 1 according to a certain theorem that we all know. That certain theorem says, okay, just remind you of that certain theorem, right? Limit from, so as x approaching a from smaller than a equals to x approaching a from larger than a. When these two limits are the same, and that's a necessary, that's sufficient and necessary conditions for the limit of the function equals to the same number, which is x approaching a equals to L. And in our case, the L is equals to 1. Okay, so these limit from left. So we clearly see that you know how to apply the theorem. That's what you want us to, you want to show us that you understand the theorem. That's why you do the left limit, right limit, and left limit from 0, right limit from 0 equals to same number. Therefore, the limit at 0 is equals to 1. When you express it, you should have negative sign on the shoulder, positive sign on the shoulder. Okay? Now, the next question. What is the function's value at 0? What is the function's value at 0? To determine that, you have to know where the function is, whether function is defined as 0. The function is defined as 0 under this rule, cosine x. So cosine x, so that's going to be cosine 0. Okay, cosine 0. And cosine 0 equals to 1. I found some mistakes. Some people write it this way. Some people read it this way. Oops. If they write f of 0, they write f of 0 equals to cosine x equals to cosine 0. I view this as a mistake, as a careless mistake, because cosine x is the entire piece of function, which is defined on the entire number line, and cosine 0 is just one number. But when you write something like this, your intention may be to, you understand you're going to substitute x by 0, but you should remove this piece. You should remove this piece. All right, so let me mark it. Right here, okay? So you should remove this piece. All right? This is f of 0 equal cosine 0. If you insert cosine x there, that's a mistake. That's a mistake. All right? They're not the same. You're telling something that's not true, because that is not true. All right, let's look at the point pi. Okay, so let's look at that point pi. I'm going to bring this picture with us so you can have a better view of it. Okay. So at pi, what happened at pi? When x is approaching pi from smaller than pi, the rule, right? So approaching pi from smaller than pi, the rule of cosine is going to apply. Okay, so this is going to be limit as x approaching pi from smaller than pi. And that's going to be cosine x. That's a direct substitution. Cosine pi equals to -1. And when x is approaching pi from larger than pi, right? So this rule, sine x, will be the rule. All right, so our next step for this piece is going to be sine x. Direct substitution, sine of pi is 0. Okay, so limit from left to pi and limit from right to pi are not the same. So the limit at pi does not exist. Okay, D and E. Because, okay, you can mention the reason. You can mention the reason if you wish. Okay, even though it's so obvious. As we said, we just want to point it out the most obvious to make our case, Okay, so that's the limit part. The limit at pi does not exist. What is the function's value at pi? Okay, so you can always go back to the original function when f is defined at pi and the rule is a cosine. Okay, so f of pi is cosine pi, which equals to -1. Okay, all right. So we are looking at, you know how to express these mathematics concisely. But in the end, how much work do you really need to, your teacher really like to see? Okay. In terms of how much work we need to show, you don't need to show this much. Okay. Some of these should stay in the splash paper. For example, this piece, you don't have to show it. But if you show it like this, it's fine. Okay, but if you remove it, it's fine. It's fine. It's okay too. And so that's it. Pretty much, you just throw each line like this. Okay, then you're done. You're done. Okay, and this is totally optional. If you don't show it, it's no big deal. Okay, we just want to see if you know how to read piecewise functions and know how to evaluate it. The next question, okay, involves absolute value. We need to consider limit from left and limit from right because the absolute value of x minus 2, of course, the domain is not x, is x not equals to 2, right? So this function makes a piecewise function. There are two pieces. Okay. For these two pieces, if x minus 2 is larger than or equal to 0, then that means x minus 2 is positive or 0. The absolute value of a positive number or 0 is the same. If x minus 2 is negative, then the absolute value of a negative number is its opposite. So we got these. Okay. And if you like to write in another form, all right, so you can solve this inequality, so that would turn into x is greater than or equals to 2, and the other one is x is going to be less than 2. Okay, so we need this, and so we will have these two cases when we deal with these. Obviously, the denominator will have a different look when we take limit from left or right. That's why we need to have two pieces. So one is from smaller, okay, and the other one is from larger. So this represents we're taking limit as x approaching 2, if you like to draw a number line, right? So at 2, we have case that, you approach x from smaller than 2, which is this limit. And this case is we're approaching 2 from larger than 2. So these are the two limits we're considering. Okay. On the first one, when x is approaching negative 2, you can jot it down like on your scratch paper. Okay, I use the think out aloud. Right, think out aloud. On this piece here, these two software don't talk to each other. Okay, so when x is approaching negative 2, it's meaning x is approaching 2, but x is smaller than 2. If x is smaller than 2, x minus 2 is less than 0. If x minus 2 is less than 0, then the absolute value of x minus 2 is going to be fitting in this form. Okay, so the absolute value of x minus 2, which is a negative number, is going to be its opposite. So that's why in this case, when we are approaching 2 from smaller, the denominator can be substituted by its equal in this case. And the numerator can be factored. Plus 3 times x minus 2. Okay, because x approaching 2 from smaller than 2, and x is not 2, and x minus 2 is not 0, so these two can be reduced. So we'll be left with a negative x plus 3. So this whole thing, it turned into negative x plus 3. And then it's a direct substitution, so we just substituted x by 2 plus 3. That's equals to negative 5. Oops. All right. So that's the limit from left of 2. How about the limit from right of 2? For limit from the right of 2, okay, once again, you can jot it down on your scratch paper. 1x approaching 2 from larger than 2. Okay, that means x is larger than 2. X larger than 2 means x minus 2 is larger than 0. Then the absolute value of x minus 2 is going to be the same as x minus 2, right? So in this case, we get the following. The denominator will be substituted by, in this case, the same as x minus 2. The absolute value is dropped. We can still use the factors and reduce. 对呀。For reduction, okay. So the right hand side, so the next step is just x plus 3, right? And substituted by direct substitution, 2 plus 3 equals to positive 5. Okay, positive 5. So now we get the limit from left of 2 and the limit from right of 2. Okay, and they're not the same. Okay, next you can say because the limit from left, okay, you can say because the limit from left is not the same from the limit of, it's not the same from the limit from the right, right? Then you can say this limit does not exist. I'm using a lot of copy and paste because I can. Okay, you have to write it down. Does not exist. That's it. But how much work do you need to show? Okay, how much work do you need to show? Do you need to show this? No, you don't need to show that. Do you need to show these? Optional? Really optional? Okay, because your work can be seen from these details. So the amount of work you really, and think out aloud, just keep it to yourself. Okay, keep it to yourself. But make sure you how to express it properly. So the amount of work you really need to show is just this much. Okay. The reason we don't need you to show this, maybe for yourself, if you need to be reminded of these two cases, go for it. But usually your reader will see redundancy, right? Because here you already expressed that part. So you don't need to express it over and over. Okay. All right, that's all for this lesson. Thank you so much. Thank you for watching.